lecture 3 in the second section of the course on organic contaminants in the subsurface environment. In the previous 2 lectures, we introduced the idea of monitored natural attenuation, making use of the natural processes. We identified the 4 natural processes, and we made some advance in advection. We showed how hydrogeologists can calculate where and how fast the groundwater is moving. We indicated that our monitoring has to be very good or we might make some mistakes. And this lecture we want to carry on that theme, emphasizing advection and some of the problems that we might encounter. There is some advice by experts about how much monitoring you need to avoid the sort of mistakes we've been talking about. And here's a diagram taken from one of those expert references. As you can see, they're suggesting that somewhere between 5 to 9 wells may be required at a typical contaminated site, a gasoline delivery station or some small source like that. And you can see they're distributed in order to try and capture plumes that might be moving away. Let's take that example and compare it to a couple of plumes. In particular, a plume from Vandenberg Air Force Base in the US. Would this sort of design actually capture that plume adequately? Here's the distribution of the Vandenberg plume plotted at the same scale as the advice document uses. You can see the plume does something funny. It moves off to the left after traveling along. And you have to believe that plumes are actually very intelligent. They'll do their best to avoid the monitoring wells. They're probably as smart as hydrogeologists. So in this case, you see the plume has done a very nice job of fooling the hydrogeologist in thinking that it's moving straight ahead, and then it makes a left turn. And you notice that now it's moving in a direction that is not being monitored. So that's an issue that we have to try and avoid. So we should always anticipate that plumes are quite narrow and quite smart. So they'll do their best to get through the monitoring network, and it's a hydrogeologist's job to design a network that is difficult to get through. Site-specific, it's experience-based, and that's the job of hydrogeologists. So let's look at a case of badly monitored natural attenuation that I was involved in. It's a research site. It's actually a real site in Canada Forces Base Borden in Ontario. This is probably the world's most highly characterized aquifer in terms of contaminant issues. The site is operated by the military, and they had a leaking underground storage tank, as you see on the left, and the site is labeled P52. In the same area, there's a site that was operated by an oil company, and their site was also contaminated, and it was cleaned up with a large remedial effort. Meanwhile, the P52 site wasn't really cleaned up, and natural attenuation was being investigated, and we took part in that investigation. The groundwater at this site always flows towards the north, so we had a good idea of which way the plume would be moving. The wells were installed previously, and they had confirmed the general flow direction. We came along and we were doing some research, but also we were trying to help the military understand whether monitoring natural attenuation was a good solution for their contamination. The difficulty at this site was the consultants gave us their report, and they showed the groundwater was actually moving in the other direction. That was surprising to us, and we wondered if perhaps they had made their measurements when they were pumping water or interfering with the system. So we discounted their values. Being academics, perhaps we were a little bit naive in doing that. We knew our flow direction, and we thought theirs was wrong. So as time went on, we developed a conceptual model for the site, and here it is. The shallow material is a sandy aquifer, one that we have done lots of research in, underlain by till, and then there was a deeper aquifer that in fact the base was using for some of their water supply. We knew where the contamination was, and we knew that it would move along the water table, or the dissolved plume at least would move along the water table and go north as we anticipated. So we saw source, we expected a plume, and the question was how far was that plume and what was happening to it. As time went on, we got more monitoring wells, we identified the source zone that you talked about in the first section of the course, and it turned out that the groundwater flow direction seemed to be changing. It was veering a little bit to the right in this case. And so our actual flow path was now going away from where we expected. It wasn't a problem, we still had monitoring there, but it was moving in an unexpected direction. We went back to the consultant's report and we noted that their plume was moving identically or to the same place that our plume was moving to. And that's a problem for hydrogeologists. There's something called conservation of mass, and if a lot of water is moving in one area, it has to go somewhere. Well, perhaps it was evaporating. We could find no evidence. Perhaps it was moving across in maybe to the east and west. Again, no evidence of permeable pipelines or anything like that that would cause that. And the only other way was down. But we were confident that the aquitard was consistent. Everywhere we had encountered it, it was consistent. Finally, our colleagues decided to investigate this situation. We had two plumes coming together. We had no explanation for where they went after they came together. They drilled a well, and as you can now imagine, they found that there was a hole in the aquitard. We saw that in the last lecture. We're now seeing it in reality at this site. Perhaps we should have known that because the sand material is glacial fluvial. Fluvial is rivers. Rivers erode aquitards. So we should have perhaps been alerted to the possibility. But we were naive and hadn't been. So this new borehole told us that our conceptual model of the hydrogeology was wrong. We had a hole in the aquitard. We already knew that the vertical gradient in the area was downward, so we're now very worried that our plume is going into that hole. This is the only hole we've seen in this area, but it has alerted us to the possibility that more holes in aquitards exist. So here's our situation in terms of the monitored natural attenuation story. This didn't affect our research, but it did affect our interpretations leading towards monitored natural attenuation. So we had contaminants, small amount at low concentration, moving into the water supply aquifer and potentially then moving to the drinking water well. The well was 2 kilometers away, and lots of good attenuation could happen between the hole and the well. But again, we needed to have some confidence that the situation might still be okay. We applied a very simple concept. It's so simple that it's clearly got a large uncertainty. But what we looked at was this sort of scenario, where we have a plume coming down through the hole in the aquitard, 2 kilometers away from the water supply well, and we can consider that plume as part of the water flowing to the well. And all of the water flowing to the well in this very simple geometric model was flowing through a cylinder that had a radius of 2 kilometers. So we had a very small plume coming up against that cylinder, providing a small area of that cylinder being diluted by all the other water coming from around the cylinder. And that's far too simplistic. Real hydrogeologists would do a better model of that, but we're probably at least order of magnitude correct in this case. So we can calculate the dilution of that plume by the time it gets to the drinking water well. And we did a calculation of the area, and of course the plume is a very small proportion of the area, very high dilution factor, so the concentration we might expect to see in the drinking water well is less than 0.1 micrograms per liter. At the time of the study, that sort of concentration would not be detected. The drinking water standard in this area is about 5 micrograms per liter, So in our mind, the expected concentration was so much lower than the drinking water standard that it was unlikely we would cause a problem if we did nothing. That is, if we did monitored natural attenuation. We're quite confident that additional removal by that last process reaction would occur. So this is a very conservative estimate of the concentrations. The concentration will likely be much lower by the time it gets to the well. The question then for you or for anybody is, are you satisfied with an analysis? Do you need to do more monitoring, or do you need to take some action now? For example, if you thought this posed too big a risk, you might start pumping some of the contaminated water away and treating it. If you were highly concerned but optimistic that attenuation would be significant, you might try monitoring it. But that would be expensive and technically quite difficult. So my understanding is the approach was to carry on with unmonitored natural attenuation. Other than monitoring the water supply well, I believe quarterly, which is what they were doing anyway. So they're alert to the potential for the problem, they're alert to stop any exposure if it does occur, and they're fairly satisfied that this is a reasonable solution. So, what did we learn from this sort of example? Well, we learned that monitoring a plume for natural attenuation really needs the correct hydrogeology. The minimum number of wells or the minimum study in many cases simply won't be enough. Again, aquatards, which we're depending on, often have holes in them, and plumes are smart, they'll find those holes. So it's a risk for hydrogeologists. And even when we do make an error, as I've just shown you, it looks like monitored natural attenuation is often robust enough to still be a reasonable solution. But again, it's a very difficult technology to apply because it depends on our monitoring and understanding of processes. And we learned, I think, that in monitoring there's considerable uncertainty. We've only looked at a few examples where plumes avoid monitoring wells, but we haven't looked at the issues of how contaminants change over time, and those issues will become important, and we'll deal with some of those in the subsequent lecture.